In this video, we're going to start covering the topic of hypothesis testing, which is one of the most sort of dreaded topics on the CFA Level 1 exam within the Quantitative Methods section of the curriculum. If you enjoyed this video, please do subscribe to the channel, and maybe you'll even want to become a member, a supporting member of the channel, and join it to get access to the full range of videos available. Right, let's get cracking with the topic. Hypothesis testing is all about taking a sample statistic, so often we cannot measure a certain parameter for the entire population. The best we can do is get a sample, and from that sample calculate, or based on it, calculate what we call a sample statistic. For example, a mean value, which we typically denote as X bar. And on that basis, we'll try to draw conclusions, inferences. So we want to infer about the population, or the true value of that parameter in the population, the mean of the population, for example. So this is a bigger set. Let's call this the population. And we want to ask ourselves the question, well, what's the true population parameter? With with samples we talk about statistics, with populations we talk about parameters. And if you're thinking about the mean value here, we denote it using the Greek letter mu, which looks like this. And the question is, what does the value of the sample statistic tell us about the true value of the population parameter, which we cannot directly measure? Now, in later videos, we're going to go through plenty of finance-based examples, which also kind of similar to those which feature in your curriculum. But I wanted to get this video this series off to a start where we don't actually dig deep into a finance-based example. It's going to be a sort of completely non-financial, non-finance-based example. Imagine we've got a factory that makes food, right? That produces some kind of food, and the ingredients that have to go into the recipe need to be dosed very sort of specifically, very precisely. That's the word I was looking for. So you've got a machine which doses food ingredients. Okay, and a specific ingredient, should be dosed in a specific weight. Let's say this specific weight is precisely 3.5 grams, 3.5 g. Okay. Now, every day or periodically, there is a sample taken from the doses that were actually administered. So a sample of 36 such doses, and you'll see why I use the number 36. It's to do with the ease of square rooting, or taking the square root of this, is taken. And today's sample reveals a mean weight, so has a mean average weight equal not to the desired 3.5 but 3.49 grams, so a little below the target of 3.5. Right, this is going to be an example of our sample statistic. The fact that we measured 3.49 as the mean weight of those 36 samples, that's going to be our X, an example of the X bar. And we want to ask ourselves the question, well, what does that tell us about the true population mean? What's the mean of everything that we produce that we're not probably are unable to measure due to the sheer quantities involved and the speed at which they roll off the production line? Okay, what else? We don't just have a mean weight, it also has a standard a sample standard deviation. So within the 36 components of that sample, 36 doses, we calculate all the weights, we produce a mean value, but we also have a sample standard deviation, has a mean weight and sample standard deviation, which is going to equal 0.03 grams. Right, we typically denote this as S, the sample standard deviation, as opposed to Greek letters, which we use when we talk about populations. Good. The question is, what should we do about this result? Does this give us grounds to stop the production line and recalibrate the machinery, or do some maintenance on it, repairs, whatever, right? This is what hypothesis testing is all about, and I'm going to walk you through the whole process as it is discussed in the book, and throw in a lot of kind of information as we do this, including info on something called the student's T distribution, which is very critical to testing hypotheses concerning mean values, and we'll be using that quite a lot in further videos as well. But please bear in mind, and we'll talk about errors, type 1 errors, type 2 errors as well. But please note that all of this stuff will be bounced around and juggled around in subsequent videos as well, where we go through further and further examples. Right, so what's this step number 1, the first step in conducting any hypothesis testing? Well, you have to state the hypotheses. And I intentionally tried to make it sound plural. I didn't say hypothesis, I said hypotheses, because I mean more than one. There's actually 2 hypotheses that you need to state. One of these is known as H0, or that's how it's denoted. It's actually pronounced as the null hypothesis. And there's going to be another one, which we call HA, that's known as the alternative hypothesis. So, and HA, the alternative, hence the A, hypothesis. The null hypothesis is what we suspect to be incorrect. To be incorrect, wrong, the one we think we're going to have to reject, or actually the one that we want to reject, in the sense we suspect it's wrong, so we want to reject it in favor of the alternative. Now, our daily sample of 36 doses has revealed something worrying, that the sample mean is below target, is off target, and hence we suspect, therefore, that the true population parameter, the true weight of the doses, is not 3.5 grams. This is what we suspect to be the case. So we state H0 as the population mean. Remember, this is the letter mu, the true population parameter, the true population mean. Population mean is denoted with the letter mu. This is the sample mean, x bar. Now, we suspect that the true population mean is not 3.5. So we write H0 as mu equal to 3.5 grams because we suspect this to be incorrect, and we think we're going to have to reject this hypothesis. It is complicated, to be honest, but this is one of the things you have to learn, because you may get questions concerning the statement of the hypothesis alone. Now, to maybe easier task, H0 always absolutely always contains one of the following signs: the equal sign, the greater than or equal to, or less than or equal to. So there is always an element of equality in the H0 in the null hypothesis. Now, the alternative hypothesis in this case is simply that mu is different to 3.8 grams, and the thing to appreciate is that H0 and HA must be mutually exclusive, so that there can't be any overlap between them. And on top of that, they must collectively be exhaustive. So, exhaustive. They must, when put together, cover the whole range of possibilities. So, for example, you wouldn't be able to have, this would be wrong if you had H0 stated as mu equal to 3.5 grams and the alternative hypothesis saying that mu is less than 3.5 grams. Well, that's not collectively exhaustive, because you're you haven't got what's to the right of 3.5 grams, but it would be okay if you had H0 expressed as mu greater than or equal to 3.5 grams, and the alternative hypothesis being mu is less than 3.5 grams. That absolutely satisfies the condition, and the null hypothesis does include one of these three signs that includes an element of equality. Right, you do get questions at the end of the chapter in the relevant reading or in the relevant learning module on hypothesis statements alone as well. Okay, let's move on to step 2 now. And as I said, we will be practicing in further videos on how to state these hypotheses using more sort of finance-based examples as well. This next step is to identify the appropriate test statistic. And this is something you'll have to learn, not just the test statistic, but also the distribution that goes along with it. And this is something you'll kind of learn and memorize more than anything else. You will see, for example, that when testing a hypothesis concerning a mean, a single mean, like the mean weight of doses applied by a food processing machine, something like this, right? For a test of what is effectively a single mean, there'll be tests when we're testing where the object of the test is more than one mean. We'll also be testing things like standard deviations, etc., etc. The appropriate test statistic is something called the t-value, and it comes from using what's known as the student's t-distribution, which is very often used in statistics, with n-1 degrees of freedom. Sometimes we'll be using n-2. This is with n-1 because we're testing a single mean. Now, in theory, if you studied statistics, you would know that it's potentially okay in this case to use the normal distribution and something known as the z-value or the z-statistic, but your curriculum for a couple of years now has been insisting on using the t-statistic and the student's t-distribution, so this is what you have to stick with, even if you know something else theoretically could be used. Now, I'm going to write down the formula because this t-value is computed as t equal to x bar minus mu from the null hypothesis divided by s, which is scaled by the square root of n. Now, the inputs we already have actually. X bar is the mean calculated from the sample. And we've got it over here. I said this is x bar 3.49. So this is this sample mean. And it will be easy to plug in the right value. Mu 0 is the hypothesized in the null hypothesis population mean, which we think is incorrect, 3.5. So the hypothesized mean. S is the standard deviation of the sample, so the sample standard deviation. And this is, of course, n, the sample size. Now, collectively, what you've got in the denominator of the fraction here, and you'll notice if you've watched previous videos that I've done on sampling and the central limit theorem, there's an important video there where this gets explained. This is known as the standard error of the sample mean. And it's a very important thing in statistical inference. If you don't remember, you can go and watch that video. If you don't have time, don't worry about it. Just appreciate that this is what it's known and it's really useful. Effectively, what will happen here is the following. We'll take the result that we've got from the sample mean, and we'll see how far it is away from the desired 3.5 grams. And given that the sample mean came in at 3.49, actually, let's change this to 3.48. Let's make it a little bit more radical, right, to give a bit more space here, give a bit more difference. Given that this is now 0.02 of a gram, we're going to see how far this is in terms of standard errors. So what this really tells us is how many standard errors is the sample mean. In our case, that was 3.48 grams away from the hypothesized mean, 3.5, and the logical conclusion is the further it is away in terms of those standard errors which feature in the denominator of the fraction, the more likely it is that we'll have to reject the null hypothesis. Okay. But that's enough for step 2. Please note that I haven't even yet calculated the value of the test statistic, although I could have, but I'm going to leave it until a later step. Now, let's just check whether I've got this corrected to 3.48. Good. And I don't think I've got that result anywhere else written incorrectly as 3.49, given the change that I made. Right, let's move on to step 3 in the whole process. This is very critical, i.e. specify the level of significance. And as we will talk about later in this video, the level of significance is associated with a certain type of error. It is in fact the probability of committing a certain error or making an error, of making a so-called type 1 error. A type 1 error is all about rejecting the null hypothesis, so rejecting H0 when it is in fact true. So in this practical case, it would mean, okay, we too eagerly reject the null hypothesis, we stop the production, we try to fix the machinery, but it turns out we didn't really have to. We too eagerly rejected the hypothesis that it is in fact, the dose is in fact the correct one, 3.5 grams. Now the question is, sometimes it's better to be too eager than it is to live with the results of getting things wrong. So it really depends on the context, as we'll say also later on. So the level of significance is typically denoted with the symbol alpha. And I'm going to assume, here, that we're looking for a 5% level of significance. So we're okay with making that likelihood of the type 1 error being 5%. And we're going to be using a two-tailed test. The fact that it is a two-tailed test comes from the fact that our null hypothesis has equals in it, just equals, not greater than or equal or less than or equal, just equals. In other videos in the future, we'll be doing one-tailed tests as well, but this is going to be a two-tailed one. Now, and just in case you're wondering where did he get the 5% from, well, I came up with it from the top of my head. This is an example which I'm making up as we go along, and you saw that I corrected some things as well as I went along to make it more extreme, to give it a bit of oomph, a bit more sort of spice. If you can have spice in hypothesis testing, this is it. Right, now, step number 4, state the decision rule. Now, I'm walking you through a very formalized process. Later on, when we do videos for sort of more financial tests, I'll try to stick to this process as well, but you'll see I don't necessarily go through it so sort of mundanely, right? Okay. Now, this is where we get to the student's t-distribution, which I said we're going to apply. And if you haven't seen this stuff before, this may seem extremely overwhelming, but you'll get the hang of it, don't worry. Don't have to be a mathematician or a statistician to appreciate what's going on and be able to apply this. The student's t-distribution, which I'll talk about formally in just a moment as well, is a bit like the normal distribution in the sense that it's symmetrical. So it's a bell-shaped curve. It's centered around 0, and as I'll later write, it's got fatter tails than the normal distribution. So it looks like okay, I didn't get that right. Wait, it looks like this is my computer trying to correct my curves and trying to make them into straight lines. Okay, well, let's break this down. One half of the curve, the other half of the curve, more or less okay. So I had to cheat my computer there. So here's an imaginary line running straight down the middle to separate the two halves of this distribution, and it's centered around 0. Now, the thing is, we want to check how far away from the 0, from the middle, we would have to go so as to have 5% probability left in the tails here. But because we're doing a two-tailed test, I'm going to split that 5% into two halves and say, ooh, how far do I need to go from the center so as to have 2.5% probability left in either tail, which collectively gives me 5. If I were doing a 5% significance test with a one-tailed 5% significance level test, I would only care about 5% being stuck in the relevant tail, not in this case. Right. I now have to make use of a statistical table. To be honest, you may have to do this in the exam, but probably not. However, to appreciate how all of this works and appreciate the examples which are given you in your book, you have to go through this at least once. what I've pulled up over here is the relevant statistical table taken from your curriculum. It sits there as an appendix within the quantitative methods of the section of the curriculum. And look, it's the relevant table for the student's T distribution, which I flipped by doing a 90% degree turn to it, because in your books, it's, if you've got the printed version of the book, it's sort of vertical, so you have to twist the page around to view it. Right, what we've got on the left-hand side are the degrees of freedom. Now, this is the parameter that defines the normal distribution, and later I'll tell you more about it. But for now, let's just recall that I wrote somewhere here that we will be using the student's T distribution with n minus 1 degrees of freedom. N is the sample size. So in our case, that was 36. 36 minus 1 equals 35 degrees degrees of freedom, df, sorry, right, degrees of freedom. So back to this table, and let's look for the right level, the right number of degrees. Well, starting with 1, as we go down in this first column, we get all the way down to 30, which is not enough. And now we scroll over to the sort of the right hand side, and over here you see 35. Brilliant, bingo. So this is the row we should be focusing on. And now, given what I said before about wanting to have 2.5 probability stuck in the tails, in either tail, I need to look for the right column. This is the column over here where I see 2.5. Well, I see 0.025, but that corresponds to 2.5 in the tail. And this is a table with one-tailed probabilities over here. So absolutely, in a single tail, not in both tails added together. See this, 2.030, this is going to be my so-called critical value. Effectively, well, let's check what it was once again. It was 2.03, that's the one, okay. What that table tells me is the cutoff point known as the critical value point, lying respectively to the left and to the right symmetrically of 0, is either minus 2.030 or plus 2.030, and this is measured in standard errors. So this is plus 2.030 standard errors from 0, this is minus 2.030 standard errors. If this is now important, because if we calculate the test statistic, the t value, which we haven't done, we just know what the data is going to be, but we haven't done it yet, and it turns out that it's greater than, more negative lies to the left of 2.030 or to the right of plus 2.030, we shall reject H0 if our computed value falls into that territory in the tails, either on the left or the right. However, if it's not big enough, either positively or negatively, to fall into those tails, so it's somewhere sort of within this area in the center, so to speak, we will we will not reject, we will fail to reject H0. This is what we do in statistical inference. So basically what I've done is I've stated the decision rule. I now know when I will reject the null hypothesis. Alternative, when I will fail to reject it. By the way, you never actually accept HO, and we never accept HA, the alternative. We either reject H0, but we don't say I therefore accept HA. No, you reject H0, or you fail to reject it, but you don't say I accept it. All right. Statistics for you. Right. Now, let me also write that the critical value that we calculated is plus or minus 2.030, and this comes from the statistical table, right? There's no way you can know this from anywhere else than statistical tables. Let's move on to the next step. That was step 4, so the next one is step number 5. Don't worry, there are only 6 steps, so we're past the halfway point, definitely. And step 5, formally, in your book, says collect data. So do the actual sampling. Well, I've actually got the data already. That's done. In theory, you should design your hypothesis test first, state the decision rule, and then get the data. That's the proper way to do it. And compute the relevant statistic, t statistic in this case, the test statistic. In our case, it's the student's t distribution, so we've got a t value statistic. Let's see. So we identified the test statistic as being t, and let's just write this down one more time. T will equal x bar, the sample mean, minus the hypothesized mean, which was 3.5 grams, divided by S, the sample standard deviation, divided by the root of n, sample size. That's why I chose 36 as my sample size, because that makes for a nice square root 6. Okay, so once again, what did we have? We had 3.48 as the sample mean weight. The hypothesized value was 3.5, so 3.48 minus 3.50 or 3.5 divided, now I don't remember the S, let's have a look again. It was 0.043, the sample standard deviation. 0.043 divided by the square root of 36, so basically 6. And now I'm going to take my calculator, but I'm not going to display it necessarily because on the screen, because this is so easy. What I'm doing, okay, well actually it's easy, but I'm going to do it anyway, seeing as other videos feature my calculator. Okay, I'll tackle what's in the bottom of the fraction, the denominator first. So I've got 0.043 divided by 36 square root. Remember my calculator is set up to handle operations under AOS mode, algebraic operating system. If you've got it set up in chain rule, I suggest you shift to AOS. There's a video on that, how to format your Texas Instruments calculator on the channel. Equals, so I've got the denominator. Now, what I'll do is I'll hit a button labeled 1 over x. Obviously, there's multiple ways to do this, but this does this computation, and now I multiply by the difference, open bracket, between 348 and 350, which is 0.02 negative, equals, hey presto, we've got a negative value of 2.79. Now this is not measured in grams. We had grams over here, grams over here, grams over here, so we had grams both in the top and the bottom of the fraction. So this is measured in standard errors. This is the value which we got from the sample, the mean, is 3.48. The value we wanted to have was 350, and that distance, although it's 2 grams, is actually 2.79 standard errors, and this is what matters. Where is it in the sense of our decision rule? This minus 2.79 is all the way here. So our suspicions have proven true. This 2.79, the calculated t-value, the test statistic, is actually more extreme to the left than the identified critical value. So we, just like we said previously, we have to reject H0. But I've gone one step too far, or I've speeded things up. This is actually formally step number 6. Make a decision. Based on everything so far, make the decision, and that decision is to reject H0. Now let me say, this does not mean we accept the alternative hypothesis. We do not this. We never accept or state that we accept the alternative hypothesis. The only thing you can say is that you reject H0 or you fail to reject it. Those are the only two meaningful outcomes that we can draw, right? Okay. Now, I want to, for a moment, go back to the statistical table and show you that we also could have rejected the null hypothesis at an even more demanding significance level, or level of significance. Look, if I go down to the right over here, where I've got 0.05, so that's 0.5% in one tail, which would collectively give 1% for the two tails combined, I would have had a value that was 2.724, which is, of course, over here somewhere, 2.724, but my computed test statistic would have been more extreme as well. So we could have rejected the null hypothesis at an even finer level of significance. And let's just state that there is a term known as the p-value. This is the smallest level of significance at which H0 can be rejected. And for us, it's going to be close to 1% for a two-tailed test, although it's probably even a little bit lower than 1% because we clear the threshold at 1%. Now, some additional remarks which I want to make, okay? Some of them are included in this reading, others are things I think you should know to help you along the way, especially when you're using the student's t distribution. So let's start with this. So the student's t distribution is symmetrically centered around 0. That's why over here I drew this bell shape with a 0 in the smack in the middle, right? It's defined by degrees of freedom. Degrees of freedom. And in our case, this kind of test, as the degrees of freedom, we used n-1, but you saw over here that the df is basically what we look at first to get us into the right row, and once we are in the right row, we just look up the value. There's no other parameter that we need to look for first. And the thing to appreciate is that this distribution has fatter tails than the normal distribution, which you may know a little bit more about if you've studied some statistics before. But the important news is that the student's t distribution, it approximates or approaches the normal distribution as the degrees of freedom are increased. Okay? Right, so let me just focus on that point a little bit, because I think it's an important result. I'm not sure if you'll be tested on it, if there's a chance that you'll be tested on it, but I think it is important nevertheless. The normal distribution and student's t distribution are both symmetrical, and if you drew one and the other, the shape could be similar. It all depends on the degrees of freedom. Now, let's draw any odd bell shape curve, okay, like this. Let's say that this is the student's t distribution with degrees of freedom at a relatively low level. What happens is, as you increase the degrees of freedom, you make this distribution sort of more peaked and you reduce its tails. So you'll, okay, once again my calculator wants to make this into a straight line. Okay, almost there. I'll have to break it into two halves, don't I? So 1/2, another half, better. As you can see, the tails are becoming fatter over here because we are increasing the degrees of freedom. I'm not necessarily very happy with the peak of this shape, but that's to do with the fact that I had to draw it in two goes, in sort of two halves. This is, once again, a student's t distribution. Look this up on the internet if you want to get a better drawing, with df at a much higher level, high. The normal distribution has got sort of the finest, the smallest tails of them all. So this would be, let's say, normal. I'm not very happy with the drawing, but it's what you get when the degrees of freedom approach infinity. And there's an easy way to test this. For example, if we were able to use the normal distribution and compute something as known as the Z statistic, which in theory we could have in this example, we could have conducted the same test, but for the normal distribution, the critical value, or the Z value, would have been 1.96 negative, and a corresponding critical value Z positive 1.96. I know this because when I took the exam, you had to learn a lot of these things off by heart for normal distributions, and that kind of has always stuck in my brain. If you want to have 2.5% left in either tail or 5% collectively left in the tails for a normal distribution, you need a Z value, which is 1.96. Now, please see what happens over here on the right hand side of the table as we increase the degrees of freedom. We go from the initial 2.03 and things become lower and lower and lower, and when you get to an infinite degrees of freedom number, this value drops all the way down to 1.96, which is the number for the normal distribution. Now, in theory, this happens when you've got an extremely large sample size, but that kind of defeats the purpose of doing sampling when you've got an infinitely large sample size. Anyway, the tails become thinner and thinner as you increase the degrees of freedom, and you approximate or approach a normal distribution with the student's t distribution. Now, the final bit of remarks are going to be on the topic of errors, something that I've already briefly mentioned before when I talked about the level of significance being the probability of committing a type 1 error. Well, in fact, there are two errors or two types of error one may commit or fall victim of when doing hypothesis testing. We've got type 1 errors and type 2 errors. Now, the type 1 error, which I've already mentioned, is rejecting H0, the null hypothesis, when it is, in fact, true. The second error is all about failing to reject H0 when it is false. Now, as we said, the probability of committing a type 1 error, which is denoted by the letter alpha, is our level of confidence in the test. Sorry, not level of confidence, level of significance. Apologies for that. Significance. And in our case, this was 5%. I was thinking about confidence because this is the next thing I'm going to say. There's a complementary measure to the level of significance known as the confidence level. And that confidence level is measured as 1 minus alpha. So in our case, this would be 1 minus 5% equaling 95%. So what you can say is alternatively either there is a 5% probability that I'm committing a type 1 error, rejecting the null hypothesis when it is in fact true. So basically stopping my dosage machine when I think there is an error, and I'm doing it even though in reality it proves that there was no problem. That's the risk you run into, that's the type 1 error. Or you can say alternatively, instead of the level of significance being 5%, you can say, well, I'm doing this at the 95% confidence level, so I'm 95% confident that I'm not committing a type 1 error. So you can think about the type 1 error as being stopping the machine that we talked about in the example too often than actually needed, because and basically bringing alpha down is all about preventing those situations. On the other hand, there is the type 2 error, and what you need to appreciate is that there is an important trade-off, right? If you want to reduce alpha, the probability of stopping the machine too often than needed in my case, then you unfortunately increase something known as beta. Beta is the probability of the type 2 error committing it, failing to reject the null hypothesis when it is actually false. So this is the risk that your machine is not doing the right dosing in the production line, but you fail to stop it because your tests do not. You failed to reject H0, which is that everything is fine. H0 is that we're dosing the right amount. And there is a trade-off. You will either stop the machine too often than needed, or you may not stop it enough. And the trade-off is unfortunately one that there is no good answer for it. We just have to decide what we really care about, what's critical. Is it okay to stop the machine too often because we need the dosage to be 100%. Maybe not in this application. Maybe it's not so critical. We just need to keep the production running. We don't have to spot little deviations. However, if you're, I don't know, dosing ingredients for medication, maybe then it's absolutely critical that we spot things, even minute deviations from the norm, and then we have to get alpha down at the expense of interrupting the whole production process quite frequently, potentially. So choice between what you want to optimize here and how you want to go about the trade-off, it really depends on the consequences. Okay, and let me just say that just like we have the confidence level, which is complementary to the level of significance, with beta, we also have something that is computed as 1 minus beta, and that is the power of the test, a measure that you may also be asked about.